All right, for this lesson, we are going to look at what are called isotopes and ions. Hopefully you have already downloaded and have opened up the handouts that go along with this to make sure that you are actually filling them out as you go along. Okay, so we're going to start off with talking about the subatomic particles again. We've already talked about and reviewed the three particles. We've got protons, neutrons, and electrons. So the question is, what happens if we add or subtract them from an atom? And can we even do it? So first of all, let's talk protons. We have kind of already talked about this a little bit, but the number of protons is the identity of an atom. All right, so if we change the number of protons in an atom, we change what it is. It becomes an entirely new element. So for example, if we were to look at carbon, carbon is element number 6. It has 6 protons, it has 6 neutrons, it has 6 electrons. If we remove a proton from carbon, it now has 5 protons, and it is no longer carbon. It becomes boron. So changing the number of protons in an atom changes what that atom actually is. It changes its identity. And in order to actually do that, it actually requires quite a bit of energy. And the process is not simple. We are certainly not going to be covering that in this course. If you really want to learn a little bit more about that kind of stuff, you can take some senior physics courses, which we'll get into it a little bit. All right. So for now, what we're going to basically say is protons, we can't change them. All right. We can't change the number of protons in an atom. If we change the number of protons in an atom, we change what the element is. And we don't really want to go down that road. So for now, we can't change the number of protons. Well, what about neutrons? Well, adding and removing neutrons can happen. Adding it doesn't really happen for the most part, but we can technically do that. Neutrons can't very easily be removed either, but it does happen. But what's important to understand is that most elements actually have or can have different numbers of neutrons. So while we may not necessarily be able to easily add or remove neutrons from an atom, they naturally will have different numbers of neutrons. So for example, if we have an element that has a particular number of protons, which any element will have, so for example, carbon always has 6 protons, but it can have different numbers of neutrons. All right. So those elements that have the same number of protons, so in other words, they are the same element, but have different numbers of neutrons, are what are called isotopes. Now, some isotopes are stable. In other words, they can have a certain number of neutrons and they always stay that way. The number of neutrons doesn't change, but some are unstable. And in unstable elements, the number of neutrons can change. All right, so let's talk about isotopes a little bit more. Isotopes, we will typically identify them by their mass. So for example, carbon-14, or you'll also see it written as C14, has a mass of 14 AMU, so 14 atomic mass units. Now, C14, carbon-14 specifically, is actually unstable. We actually use carbon-14 to identify the age of objects that contain organic material. So you've probably heard of the term carbon dating before. It comes from this particular isotope of carbon. So again, carbon-14 has a mass of 14 atomic mass units, which if you look at your periodic table doesn't seem to really make sense. But here's how it works. Carbon has many isotopes. There are 2 very common ones, carbon-12 and carbon-13. Now, how many neutrons would carbon have to have in order to be considered carbon-12? And how many neutrons would carbon-13 have to have in order to be considered carbon-13? Well, remember, this number refers to the atomic mass. So carbon-12 has an atomic mass of 12. Carbon-13 has an atomic mass of 13. In the previous slide, we talked about carbon-14. Carbon-14 has an atomic mass of 14. Well, where does the mass of an atom come from? All right, so carbon-12 has a mass of 12. That means it has 6 protons, and that means the number of neutrons is equal to 12 minus 6, so the mass minus the number of protons, which means 6 neutrons. Well, what about carbon-13? Carbon-13 has a mass of 13. Well, so that means that it has 6 protons, because carbon has 6 protons. And so if it has 6 protons and its mass is 13, 13 minus 6 means it has 7 neutrons. Carbon-12 has 6 neutrons. Carbon-13 has 7 neutrons. So we can see the two different masses are coming from those different numbers of neutrons. Well, let's take a look at the periodic table. Isotopes are the reason that the mass numbers on the periodic table aren't whole numbers. So if we look back at that example of carbon, you'll notice that the atomic mass of carbon on the periodic table isn't 12, it's 12.01. And that is because the atomic mass that we see on the periodic table is the approximate average mass of all of the possible isotopes of that element in the universe. So there's carbon-12, there's carbon-13, there's carbon-14. There are actually, if I remember correctly, there are actually 16 different carbons that are possible. Right? There are 16 different masses of carbon that you can find. And it's all because the number of neutrons is different in each particular type. But if we were to take all of the carbon atoms in the universe and find the average mass of all of them, it would average out to about 12.01 atomic mass units. All right? Now, we keep talking about different carbons. So carbon-12, carbon-13, carbon-14. Notice every one of them is carbon. So we can change its mass, we can change the number of neutrons, but we don't change what it is. It is still carbon. Okay? Now, protons, we've said we pretty much can't change that because then we would just be changing the identity. Neutrons, we can change those, but it still stays as carbon. Now the question is, what does that change as far as how it reacts? Well, it doesn't. Right? So carbon-14 and carbon-12 and carbon-13 are all going to react pretty much the same as each other. But what about if we change the number of electrons? If we add or remove an electron from an atom, it still stays what it was. Right? So just like what we saw with neutrons, carbon, if we change the number of neutrons, is still carbon. If we change the number of electrons in carbon, it's still carbon. But what's going to change is what's called the charge. All right, so that is what brings us to the next part of this lesson, and that is what are called ions. And that's, let's see, it's spelled I-O-N-S, but pronounced ions. Ions are atoms that have gained or lost electrons. So carbon typically would have 6 protons, 6 neutrons, although we have just seen that it could have a different number of neutrons, and 6 electrons. The number of protons and the number of electrons are equal. They have positive charges for the protons, negative charges for the electrons. They balance. All right, so the positives and the negatives equal each other. If an atom gains or loses electrons, that balance is gone. So the positives won't balance the negatives anymore, and then that means that therefore the ion, the atom, will now have an overall charge to it. So far, the atoms we have seen have the same number of protons as electrons. That means the atom has a neutral charge. So any element you pick off the periodic table, so potassium. Potassium is element number 19. It has 19 protons. That means it has 19 electrons. The 19 positives and the 19 negatives balance out. So plus 19 minus 19 adds up to 0. That's a neutral charge. If it gains electrons, that means it has more negatives. So if an atom gains more negatives, it has a negative charge. If an atom loses electrons, that means it's getting rid of all of its negative stuff. It's getting rid of all of its negative particles. That means it's going to have a positive charge. This is the part that will often trip up students, because their first thought is, if I gain electrons, it should be positive because I'm gaining something. But remember, electrons have a negative charge. So if you're gaining more negative, it means you're becoming more negative, right? So if it gains electrons, it's going to have a negative charge. If it loses electrons, it means we're getting rid of negatives, which means we're going to have an overall positive charge. Now, a reminder, electrons move, right? Electrons fly around the outside of an atom. The protons and neutrons are trapped inside the nucleus. So this is actually something that is pretty easy to occur. Neutrons, a little bit harder for them to be added or removed from an atom, from the nucleus. Protons, same thing. It's not an easy thing to do, but electrons, because they're already flying around the outside, it's really easy for us to add or remove those from an atom. So now the question is, well, why? Why is this important? Why does this happen? And it comes down to being stable. Atoms that do not have a full outer shell are unstable. Remember, we've just finished looking at the periodic table. We've looked at patterns on it. We've looked at Bohr-Rutherford diagrams. We looked at Lewis dot diagrams. And we saw specifically that those patterns, the ones that we are going to care about, and I told you about this, the ones that we're going to care about are those outside valence electrons and that outer shell. And I also made mention of that final column, the noble gases. They're unreactive. They don't react with anything. And why don't they react? They don't react because their outer shell is full. And a full outer shell makes an atom stable. If you do not have a full outer shell, you're unstable. So there are a couple of options. To become stable, an atom is either going to gain electrons, which would mean it fills up that outer shell, or it's going to get rid of electrons. And because it gets rid of electrons, it can empty that outer shell, and then the shell underneath is a full one. Now, something to keep in mind when we're talking about these shells or these orbitals. These orbitals, they don't exist. There aren't physical shells or rings, right? We refer to orbitals or shells as basically just where we can find the electrons. So the outer shell of an atom is just the spot or the place where we can find the electrons in that atom. If the electrons are gone, that shell or that orbital ceases to exist, because the only reason it existed was because those electrons were there. So if an atom gets rid of the outer electrons and that outer shell becomes empty, that outer shell ceases to exist. It doesn't exist anymore. And that means that the shell underneath now becomes the outer shell, right? So to become stable, to give itself a full outer shell, an atom can add up some more electrons to its outer shell to fill it, or it can empty out the outer shell, leaving the full shell underneath. Now, you will often see that full valence shell referred to as a stable octet. And we often refer to it that way because typically when we're talking about elements that are doing this, particularly when we're first learning about them, we're learning about some of the smaller elements. So we're learning about those elements in the first few rows. And if you remember, that outer shell in the second and third row can only fit up to 8 electrons. So a stable octet means we have a stable set of 8 in that outer shell. But if it is in the first row, or if it is in the 4th row, or 5th row, or 6th row, or 7th row, it's not going to have 8 in the outer shell. But because, again, we typically are talking about those couple of rows, particularly when we first start learning about it, we talk about the stable octet. So don't let that trip you up too much, all right? Now, here's what we're going to do. We're going to draw a couple of diagrams here, but we're going to cheat. Now, in the instructions, I tell you to draw a Bohr-Rutherford diagram, but we've already learned that you don't have to draw Bohr-Rutherford diagrams anymore. Bohr-Rutherford diagrams aren't necessary because now we know how to do a Lewis dot diagram. So here's what we're going to do. We're going to draw a Lewis dot diagram for magnesium. So on your handout, there's a box. There are a couple of boxes on the right-hand side. stacked on top of each other. And in the top one, you're going to draw the Lewis dot diagram for magnesium. So remember, to draw a Lewis dot diagram, you draw your symbol first, and then you have to figure out how many electrons are in the outside shell, and then you draw in those dots. Well, magnesium is in column number 2, right? It's element number 12. So column number 2 tells us it has 2 dots around it. So that means that we have 2 electrons in the valence shell. To be stable, that atom needs a full valence shell. How many electrons does it have to gain to get a full one? Well, here's the trick. It basically comes down to whatever is the lowest number to make it easy. Magnesium has 2 electrons in the outer shell. In order to gain electrons to get to a full outer shell, it would have to gain 6 electrons, right? Because it has 2 already, it needs 6 more to get up to 8. If it wanted to lose electrons to get a full outer shell, it would have to lose just 2. Because if it loses those 2 electrons, that full outer shell in the shell underneath, that orbital that is underneath the valence orbital, would be a full orbital. So what it comes down to is, what is easier to do? Gain 6 or lose 2? And since gaining or losing a single electron is pretty much equal, in reality it actually isn't. It's significantly more complicated than that. But to simplify things, we're just going to say gaining or losing is about the same. Well, what's going to be easier to do? Gain 6 or lose 2? Well, losing just those 2 electrons is going to be easier to do. So what's going to happen? Magnesium is going to lose 2 electrons. Now, here's the tricky part. If magnesium loses its 2 electrons, how many electrons does it have in the outer shell? Well, if it loses 2 electrons, that means it now has an empty outer shell, which means the shell underneath is the full shell. And that has 8 electrons in it. So if magnesium loses 2 electrons, how many electrons does it have in the outer shell? It has 8. All right. So now the question is, what is the charge on that atom? Well, it originally had 12 protons, 12 electrons, 12 neutrons. And we can figure that out by looking at our periodic table. And we see that magnesium is element number 12. So it means it has 12 protons. And because the number of protons and electrons are equal, that means it has 12 electrons. And because it is element number 12 and the mass is 24, 24 minus 12 is 12 neutrons. Now, it started off with 12 protons and 12 electrons. We just got rid of 2 electrons. So how many electrons does it have left? It has 10. So it has 12 protons and only 10 electrons. So it has 12 positives, 12 positively charged particles, and only 10 negatively charged particles. So what is its charge now? Positive 12 minus 10 leaves us with a charge of plus 2. It has a charge of positive 2 because it has 2 more protons than it has electrons. So now what we're going to draw in the top right corner is a plus 2. All right. So in that bottom box, we're not going to draw the Bohr-Rutherford diagram. We're going to just draw the Lewis dot diagram. But in the top right corner, we're going to actually put a plus 2 to represent the fact that it has a charge of plus 2 now. All right, let's try this now with oxygen. We're going to do the same thing. So we're going to, instead of doing the Bohr-Rutherford, we're going to draw a Lewis dot diagram. So we draw a Lewis dot diagram for oxygen. Oxygen is in column number 18. So that means, or sorry, column number 16. So that means it has 6 valence electrons. All right, so how many electrons in the valence shell? 6. So if we draw our Lewis dot diagram, we've got an O in the middle for oxygen, and then we put in 1, 2, 3, 4, 5, 6 electrons around it. Now, to be stable, we need that full shell. So how many must it gain to get to a full shell of 8? Well, it already has 6, so we would have to gain 2 more. And if we want to lose all of those electrons to empty out that outer shell, we would have to lose 6 because it has 6 electrons in the outer shell. What's going to be easier? Well, again, just like last time, it comes down to the smaller number. I can either gain 2 or lose 6. Gaining 2 is going to be easier to do than than losing 6 because the number's smaller. And it really just does come down to that. So, in the bottom box, we're going to draw the Lewis dot diagram after it gains that full shell. So, we would have our O in the middle, and then now it has gained 2 extra electrons. So, instead of 6 electrons, we should now have 8 electrons around the O. And we're going to write the charge up in the top right corner. What's the charge? Well, oxygen is element number 8, so that means it has 8 protons and 8 electrons. Now, we have just given it 2 more electrons, so that means it has 8 protons and 10 electrons now. 8 protons, so that's 8 positively charged particles. 10 electrons, that's 10 negatively charged particles. So plus 8 and minus 10. So 8 minus 10 gives us negative 2. So that means the charge that will go up in the top right corner of oxygen is minus 2. All right, so doing that with Lewis dot diagrams certainly makes it easier. We have seen, how sometimes atoms lose electrons to form positive ions. They can also gain electrons to form negative. A note, positive ions that have had their shells emptied do not have dots. All right, so when we're drawing Lewis dot diagrams, we're actually not going to include the dots when we empty out a shell. So let's look at a couple of examples of what we mean for this. So first off, we draw the symbol for the element. Then we decide, is it gaining or losing electrons? If it gains electrons, we're going to draw a full octet around the symbol. If it loses electrons, we are not drawing dots around the symbol. Then next we draw square brackets around the symbol and dots, and then we put the charge outside of the brackets. So what does this look like? So for example, if I had either calcium or nitrogen, we'll do calcium first. Calcium is element number 20. It has 2 electrons in the outside orbital. We know that because it is in column number 2. We have to decide, is it going to gain or lose electrons? Well, to get to a full octet, it would either have to gain 6, or it would have to lose 2. Losing 2 is going to be the easiest way to do it. If it loses 2 electrons, it's going to become more positive. Remember, losing electrons means we're getting rid of the negative particles. We lost 2 electrons, so it becomes positive 2. Now, look at our rules. We draw the symbol. So the symbol for calcium is Ca. We then determine if the ion has gained or lost electrons. We're going to lose electrons, so we're not going to draw dots around the symbol. And then we're going to draw square brackets around the symbol. And if there were dots, we would draw them around that too. And then we're going to put the charge outside of the brackets in the upper right. And that's what it looks like. So we have the symbol is Ca. We have no dots because it lost electrons. We put the square brackets around, and then we put the charge up in the top right corner. Now you see it written as 2 plus or plus 2. Either one is fine. Our next example is nitrogen. Nitrogen is element number 7. It is in column number 15, which tells us it has 5 electrons in the outside orbital. That means in order for it to become stable, in order for it to fill up its outer shell, it either has to lose those 5 or it can gain 3. 3 is smaller than 5, so it's going to go that way. So nitrogen will have 3 more electrons, so that's 3 more negative particles, so its charge is going to be 3 minus. So to draw it out, you draw the symbol first, so it would be the capital N, and then we are going to draw a full octet around the symbol. So we're going to draw 8 dots around it to represent that filled up outer shell. And then we're going to put square brackets around all of that. And then we're going to put the charge of 3 minus or minus 3 up in the top right corner. All right. So that's how you draw a Lewis dot diagram for an ion. So if it's just a regular atom, you just draw the symbol with the dots. And those dots represent how many electrons are in the outside orbital. It looks exactly like a simplified version of a Bohr-Rutherford diagram. If we're drawing a Lewis dot diagram for an ion, we have to show that it is either filled up or emptied out its outer orbital, and we do that by either not including any dots or including all of the dots to fill up that outer shell, and then we draw square brackets around it, and then we put the charge up here. All right, there's no charge on a regular atom, so we don't include this. We only include that charge when we're talking about ions. All right, now, 2 different types of ions, 2 different names. The first is what are called cations. That's just simply a positively charged ion. A couple of ways you can remember it. You can remember that a cation is positive because it's the letter T in cation resembles a plus sign, or you can just remember that cats are positive. That's usually how I remember it. If you like cats, then you'll remember that cats are positive. If you don't like cats, well, just remember that when it comes to chemistry, that idea is wrong. Cats are positive, right? Anion is the other type. An anion is a negatively charged ion. So the N in anion will tell you negative. It's not the greatest way to remember it, but it's probably the best way you're going to come up with. Naming those ions, these ions actually have a name. So when an atom gains a charge, it changes its name slightly. For metals, so those elements that are on the left-hand side, metals are always going to lose electrons. And they are going to just simply be called by their name. So it's just the name of the metal with the word ion after it. So sodium ion, magnesium ion, potassium ion, lithium ion. All right. So if it's a metal, the ion name is just the name of the metal with the word ion after it. Non-metals, we do something a little different. What we do is we take the first syllable and cut off the rest and add IDE. So for oxygen, it's oxide. For sulfur, it's sulfide. Chlorine, chloride. Nitrogen, nitride. Phosphorus, phosphide. Hydrogen, hydride. All right. So the oxygen atom will produce an oxide ion. Sulfur atom, sulfide ion, and so on. So again, metals, it's just the name of the metal with the word ion. For non-metals, it's the first syllable plus IDE, ion. Symbols, we don't actually need the full symbol. So we looked at the example of magnesium and oxygen, where when we draw it out, we've got the square brackets, and if it's filled up, we add in the dots. We don't actually even need that information. All we actually need is the symbol and the charge. All right, so when we're writing out ion symbols, all you write down is the element, symbol, and the charge that comes after it. Now, when does this happen? So we should now understand that in order to become stable, an atom is either going to gain or lose electrons. But the question is, when? How? Like, how does this even happen? Where do those electrons come from? Where do they go? What then happens after they gain or lose electrons? That is what the next topic will be when we talk about ionic bonds.